Welcome all. Today our topic is cache memory. What is a cache memory? It is a memory that is there in between the CPU and the main memory, and it stores frequently accessed instructions and data. Those instructions and those data which are frequently used by the CPU, which are active, which we call as active portions of the program and data, they are stored in this cache memory. The purpose of using cache memory is to decrease the average access time of instructions and data. By doing that, we can save a lot of time of the CPU. There is a property which we call as locality of reference. This property states that if we take a certain period of time, a small period of time, the addresses that will be generated by a typical program, the addresses which the CPU will seek, the addresses of this main memory which the CPU will ask for, those addresses they fall in a particular localized area. They are not spread randomly all over main memory. So it has been found that in a short interval of time, whatever the CPU asks for, whichever addresses it wants to access, wherever it whichever data it wants to access, in that there is a localization of things. So it will not usually go outside that locality. So if the CPU is asking for an address, for example, 500 address, then the next address that the CPU will ask for will be somewhere around there, around that. So this is called a locality of reference. This locality of reference property is very useful when we see the thing, this cache memory concept. Since the CPU will ask for a localized uh, addresses, that means there will be very much repetition. So if the CPU is asking for an address for a data which is at address 500, after that it asks for a data which is at 505, then 507, then there is a huge possibility that the CPU will ask again for the data of 500, and then after some time 507. So in this way, there is a certain relationship between these two things, and it has been found because of this property, the cache memory is a success. Here we can see that this diagram shows the organization, the connections, that the CPU is connected to cache memory, and the cache memory is itself connected to main memory, and the CPU can also directly access the main memory because of the bus system. Okay, now we say that how does this transfer occur? So let us go back to the previous diagram. So if the CPU asks for certain address, the CPU wants some data which is at a certain address, for example at address 500. So the CPU will say to the will generate the address. It will say 500. I need the data at 500. So first of all, the cache memory will be checked. Is this word that the CPU is asking for in the cache or not? If it is in cache, then the data is transferred from cache to the CPU. And this thing is called a hit, meaning that we have found the data in the cache. And if the data is not found in the cache, the CPU then takes this data from the main memory, and at the same time a copy of that word, that data, is put into the cache. So this is the working of this system. CPU asks for a word. First of all, this word is searched in cache. If it is there, good, then the word is transferred to the CPU, and this is called a hit. And if the word is not in the cache, we call it a miss, and then the word is taken from the main memory, and CPU takes one copy of that word and another copy is stored in the cache memory for future references. This way this whole concept works. So when the CPU refers to memory and the word is found in cache, we call it a hit, and if it is not found in cache, this is called a miss. There is a term which we call as hit ratio. What is that? It is the ratio of hits. So how many hits out of the total number of accesses, how many were hits? In other words, that if the CPU has asked for 100 words, out of 100, how many times, how many words were found in the cache? This is called hit ratio. So the formula is hit ratio is equivalent to number of hits divided by the total number of CPU accesses. And the total number of accesses will obviously be equal to the number of hits plus the number of misses. So this will be the formula. Let us take up a numerical problem on this concept of hit and miss. So the problem says that we have a cache memory, its access time is 100 nanoseconds, and we have a main memory, its access time is 1000 nanoseconds. Fine. So the cache memory is in this numerical also is showing that it is faster than main memory, and it is estimated that 80% of the memory requests are for read and 20 for write. So when the CPU generates the address, 80% of the time it wants to read and 20% of the time it wants to write into the memory. And it is given that the hit ratio for read accesses only. So this 80% for which it wants to read, for this thing The hit ratio is given, and that is 0.9. It is given. Then the problem says a write through procedure is used. What is a write through procedure? The procedure is like this. Whenever the CPU has to write something into main memory, if there is a copy of that in cache, what will the CPU do? It will write at both places. If it writes at both places, it writes in the cache, it writes in the RAM as well, which happens simultaneously. Then this thing is called write through method, write through procedure. So if the CPU writes in both the cache and the main memory at the same time, this is called a write through procedure. Okay. The first part of the problem says, what is the average access time of the system considering only memory read cycles? Okay, let us first see this A part. It is given that the access time of cache is 100 nanoseconds and the access time of main memory is 1000 nanoseconds. If we take only memory read cycles, it is given the hit ratio is 0.9, which means that 90% of the times the word is found in cache. Fine. So we say 90% of the times, that is 0.9, which is the hit ratio, the word is found in cache. And if the word is found in cache, the access time is given, it is 100 nanoseconds. So this 0.9 multiplied by 100 will be the access time when there is hit, about hits, plus the remaining 10% or the 0.1. For the remaining 10%, what will happen? There will be a miss. And what do we mean by a miss? A miss means that we searched the thing in cache memory, but we couldn't find it there. Then we access that thing from main memory. So this 100 is the same searching thing that we searched it in cache memory, but we couldn't find it there. But to search in cache memory, we need 100 nanoseconds because searching needs access of cache memory, and it is not found there. Then we need 1000 nanoseconds to get the word from RAM. And when we solve this thing, it comes out to be 200 nanoseconds. So what does this imply? This implies that if we take only read cycles, then it on an average this computer is having an access time of 200 nanoseconds. We can see here that if in this computer we remove the this thing cache, if there is no cache, the access time would have been 1000. By using cache, it has been reduced to 200. Okay, let us look at part B. What is the average access time of the system for both read and write requests? And let us now consider both read and write. It is given that 80% of the time it is read, 20% time it is write. So what is the average access time for in considering both? So B part, 80% of the time it is read. So for read we just calculated it is 200 nanoseconds plus remaining 20% of the time it is write. When we write, what will we do? We will write in main memory as well as in cache memory. Writing in main memory will take 1000 nanoseconds, and in cache it will take 100. But since both things will happen parallelly, so we need only 1000 nanoseconds. By solving this, we get 360 nanoseconds. So this will be including read and write. The access time will be 360 nanoseconds. Okay, part C. What is the hit ratio taking into consideration the write cycles? Okay, the hit ratio was given, but it was given for only read. If we consider only read, the hit ratio is 0.9. So if we consider the write also, what will be the total hit ratio? And we know that this 0.9 is concerned with only 80%. So we will multiply the two. So this 0.9 is for read. So the read, since the read is only 80% of the whole, so 0.9 into 80% will be the total hit ratio, which comes out to be 0.72. Let us move to another related topic, which is mapping. What is mapping? Mapping, it is a transformation of data from main memory to cache memory. So we have data in main memory, then we move it to cache memory. The transformation, that is called a mapping. So based on the mapping procedures, based on the organization of cache, there will be three types of mapping procedures. So how the cache is organized, what is the internal structure of the cache? Based on that, there will be three types of mapping procedures. So the first mapping procedure is called associative mapping. The second is called direct mapping, and the third is called a set associative mapping. Let us see them one by one. So here, let us try to understand what is associative mapping. In associative mapping, it happens in a cache where in which the cache is made up of associative memory. So here this diagram shows a cache. This is a cache memory. It is based on associative memory. What is associative memory? A memory in which both the address as the date and the data is stored like this is called associative memory. So this is a special type of memory where both the data and the address is stored inside the memory. So this associative memory here is used in this cache. That is why it is called associative mapping or associative mapping cache. Let us take an example. Let us say we have a cache memory which has a size of 512 into 12, and we have a main memory which has a size of 32K into 12. So based on this, let us try to understand how this associative cache will be and how will be its mapping. Since the cache memory here is 512 into 12, it means that the word length is 12, which is the same here because the same word is stored in cache. What does this 512 imply? It implies that the total words in this cache is 512, which means it will have 9 address lines, as 2 raised power 9 is 512. And what about main memory? it is 32k, which is 2 raised power 15. So the address lines of this main memory will be 15. So since the address lines of the main memory are 15, that means the CPU will generate an address of 15 bits for the accessing the main memory. To simplify things, here we are using octal system because it would have been difficult to write 15 bits here. So to simplify things, we use octal system. In actual, obviously, there will always be a binary number. So in octal system, we know that 3 bits are represented by 1. So that is why the CPU generates 15-bit address, but here we are showing only 5 bits in octal. Fine. In the same way, the data is also in octal. So it is actually 12-bit data here. So 3 bits for this, 3 bits for this, 3 for this, 3 for this. In total, there will be 12 bits of data because of this 12. Okay. Now the CPU generates a 15-bit address. The address is searched here. If this address generated by the 15 bits is found here, we say we have a hit. For example, if the CPU says 22345, this address, so there is a hit, then we have found the data here. This data will be transferred to the CPU. And if the address is not found here, we call it a miss, and the address, the word is accessed from main memory, and an entry is made here in cache memory also. Obviously, after some time, all these entries here will be filled because the size of main memory is huge and the cache is very small comparatively. So after some time, all these entries will be filled in cache. But after that, when all the entries of the cache are filled, then when a new word, which is an address and data pair, is to be introduced into cache, it will be done on a first in, first out basis. So there are many algorithms to do this job, to replace things. When something is full and a new entry comes, you have to replace it. You have to put it somewhere and move something out. And this can be done by many algorithms. One of them is first in, first out. So if this is the first entry, this will go out and the new entry will come here. Then this will go out, then the second new entry will come here, and so on, which will follow a round robin pattern. So this will be the first in, first out thing, and the way it will happen will be a round robin pattern. Means first this will be filled, then this, then in a round way, circular way, again this, and again. So it will be a round robin pattern. And we can also use other algorithms for doing this replacement thing. Let us now see the second type of cache, which is based on where we use direct mapping. So this is a direct mapping cache. Let us take the same example where we have a cache memory of 512 into 12 and a main memory of 32k into 12. So since this is 12, so the data is 12 bits, the data is 12 bits. This is 512, so the address of cache memory will constitute of 9 bits, and this is 32k, that means the address of main memory will constitute of 15 bits. Now if we put addresses here, so the first address of cache will be 9 zeros and last address will be 9 ones. If we convert this into octal for simplification purposes, so 9 zeros converted to octal will be 3000, and 9 ones converted to octal will be 777. In the same way, if we see for RAM, it is 15-bit address. First address will be all 15 zeros. 15 zeros converted to octal will be 5 zeros, and the last address will be 15 ones. And when we convert 15 ones to octal, it becomes 5 times 7. So this is our main memory, this is cache memory. Okay. What about this address? When the CPU generates an address, since here the cache is not of associative type, it is not that there is a address here and a data here. No, it is a direct cache, which implies that it has a random access here. This cache is of random access type, and it becomes cheaper than the previous one, associative cache. Why? Because in associative cache, you have a larger word length. You have to store the address as well as the data. So for every word, there will be a good amount of memory used. Associative caches, therefore, are costlier than this. And here it is a direct access and a random access. Okay, and what happens when a CPU produces the address? The address is divided into two parts. One part is called a tag, and the next part is called index. Since the address is 15 bits in this case, the 15-bit address will be divided into tag and index. How many bits the index will have? Index points to the cache. Since the cache is 9 bits address, so the 9 bits will be index and the remaining 6 bits will be tag. The logic is very simple, that this index, the 9 bits, will be searched here. In fact, we will have a random access. We will go to this location. Whatever is written here, we will go to that location. So once we reach that location, for example, if 777 is written here, we will go to 777. Then we will search for the tag here. This cache memory will consist of two parts, tag and data. So we have to match the tag also. If this tag is same as the tag here, then it is a hit, otherwise it is a miss. So let us elaborate on this thing. So here you can see a cache memory, the same cache, 512 into 12. So this is a 12-bit data, and here, unlike associative memory, there is no address, but there is tag. So if the CPU says, for example, the CPU says 02777. So in that 777 is the index. So we will go to 777. Then we will see if there is 02 written here. Yes, we went to 777. There is a match. The tag is matching. Then this is a hit, and this data will be transferred to the CPU. Now, if the CPU says 01000, 01000, that means 000 is the index. We will go to 000. Good. Then we will compare the tag. The tag here is 00, but the address says 01. So the first part 01000 of the 01000 is the tag. So 01 is compared with 00. There is a mismatch, which implies that we have a miss. So the data will be accessed from main memory. So the 0 1 0 0 data will be accessed from here and not from cache. And once the data is accessed from here, the entry will be made unto here. So this entry will be overwritten by 0 1, this 0 1, and 3450. 3450 will be written here. This cache memory can also be divided into blocks. Here we are seeing this memory in terms of words. This is one word of cache, this is second word of cache, third, and so on. This is the last word of cache. This is the 512th word of cache. And these all words can also be divided into blocks. So let us see what does that mean. So we can say this is the same cache starting from 000 and ending at 777. So we can say that those addresses which are here, which are from 00 to 00 ending 00. In other words, since this is an octal, it means the first out of 9, the first are 6 zeros, and all those addresses which have 6 zeros at the beginning, we may call them as block 0. And then the next address, which will be 000 001, all those which have this range, we may call that block 1. And then the 2 will be 000 010, which an octal will be 02. So that 02 range we call as block 2, and so on. So in this way, we can also divide this cache into blocks. So if we look at this cache, how many blocks will there be? The last entry will be 77, which means 111 111, 6 ones. So 6 ones imply 64, 64 numbers. So in total there will be 64 blocks, block 0, block 1 up to block 63. Since these addresses are the index and we have divided this address into two parts, so this 00 we use it to represent block and the remaining for word. So we can also say that the total address, which was initially divided into tag and index, now further the index can be divided into block and word. Since in this example the block is represented by 2 octal bits, which means 6 bits, so the block is of 6 bits, and the word will obviously be of 3 bits because the index was 9 bits. You can also see here that in one block, how many words are there? It starts from 0, which means 000, ends at 7, which means 111. So that means in one block there will be 8 words. So if I have to address 8 things, I require 3 bits. That is why this is 3. So this is also a direct mapping cache where we have a block size of 8 words. So the whole length is divided into 8 segments, which we call as blocks. Now let us take a numerical problem. It is related to direct mapping cache. The problem says that we have a digital computer which has a memory unit of this size. It has a cache of this size, 1K words. So the 1K is the number of words in that cache. The size of word is not given. The cache uses direct mapping, so it is a direct mapping cache, and block size is also given, that each block is of length 4 words. Now A part, how many bits are there in the tag, index, block and word fields of the address format? So first let us see how many bits are there in the tag and index. We know that we have been given that the size of main memory is 64k into 16, and size of cache is also given as 1k words. What will be the CPU address? How many bits will there be in the CPU address, the address that the CPU will produce, since this address represents the address of main memory. The main memory has 64k entries. For 64k entries, how many address bits are needed? We know that we can calculate it using log. So log of this 64k implies 16. So our main memory is 64k. That means our address will be 16 bits. This is very simple. So from the 64k, we realized that the address will be 16 bits. So the total CPU address we have calculated, it is 16 bits. In direct mapping cache, we know that this address is divided into two parts, tag and index. Now we have to find what is the value of tag and what is the value of index. Again, we know that this index represents the address of cache memory. So this index represents, since this index represents the address of cache memory, what is the, how many words are there in cache? It is 1k. So since there are 1k words in cache, how many bits are required to address 1k things? To address 1k things, we require 10 bits, which can also be found through this formula, log. So log of 1k to the base 2 is 10. So that means for this cache of size 1k, we need 10 bits, which automatically means index field is of 10 bits. So here we write index is of 10 bits. Since the index is of 10 bits, the tag automatically can be calculated as 6 bits because the total address is 16 bits. So that implies the tag will be of 16 minus 10, 6 bits. Now in the same A part, we have to calculate block and word size also. What is block and word size? We know that this index is further divided into block and word. The tag remains the same, but the index is divided into block and word. We have to find the size of these bits both. In the question, it is given that one block is of size 4 words. So since one block is of size 4 words, to address 4 things, we require 2 bits. So to address the words in a block, we require 2 bits. So we write here, this will be 2 bits. Why? Because each block is of 4 words. 4 words addressing requires 2 bits. And if it is 2, this will become 8 because 10 minus 2 is equivalent to 8. So we have found the tag is 6 bits, index is 10, out of which block is 8 and word is 2. Part B. How many bits are there in each word of cache? And if we look at the cache, what does a cache, mapping cache include? It has a tag, it has a data. So each word of cache will constitute of tag, it will have data. In this example, the data here is given 16. You can see the data is given 16 bits. So data is 16 bits. What is tag? We just calculated 6. Good. And in this B part, there is extra thing. It says include a valid bit. So what is this valid bit? In some cache, there is an extra thing called a valid bit. So here in this, we can see it. So in this cache, we have a tag, and then we have a data, and here there could be another column that is called a valid bit column, which if it contains 1, it means this word is valid, and if it contains 0, this means this word is invalid. In some cache, it could be like this. So the total word size of the cache will be tag plus data bits plus valid bit. So since it is given in the question, we have to include a valid bit. So this means that one word of cache will constitute of the tag field, the data field, and the valid bit 1. So 6 plus 16 plus 1 of the valid bit becomes 23 bits. This means that the width of the cache memory, that the one word of cache memory is of 23 bits. Part C. How many blocks can the cache accommodate? How many blocks will there be in the cache? Since 8 bits are there for the block, for naming the blocks, for addressing the blocks, we have 8 bits. So this implies the number of blocks will be 2 raised power 8. So number of blocks of cache will be 2 raised power 8, which is 256. If it would have been given that there are 256 blocks, how many bits of address are required? Then we would have said 8. Now here it is the reverse, that we have 8-bit address. How many blocks will it address? It will address 2 raised power 8, which is 256 blocks.